Welcome back, OChem 2. I'm so excited. This is one of my favorite parts of Unit 4, and in fact, it's one of my favorite parts of the entire semester. We're going to tackle 1-4 additions. This is going to take me a couple videos, so let's start by laying the foundation on what a 1-4 addition is, and let's relate it to some of the stuff we've already seen. So when we're looking at our ketones and our aldehydes and even our esters, that's coming in some later videos, we've already seen reactivity in Unit 2 and in Unit 3. And now we're going to add to that in Unit 4. So I've got this PDF posted as well up on your Blackboard, and I made sort of a little guide here on some of our reactivity. So let's do a quick review. In our Unit 2, we took substrates, any kind of ketone or aldehyde, and we really focused on the fact that a ketone or an aldehyde has that nice polar arrow. We've got a nice partial positive right there on that carbon, and we added stuff to it. We added our hydrides, and where did they go? They went right to that carbon right here. We added our Grignards. So we made all kinds of carbon Grignards, all sorts of reagents there, and they added exactly that same carbon. And we really used that carbon as an electrophile. And that was all in Unit 2. So Unit 2 is big. We had the hydrides, we had the Grignards. We also could add some organolithium compounds. So this is our Unit 2. We added nucleophiles in. We recognize that what I've labeled here is this number 2 carbon is a good electrophile. Let's write that out. And so our whole Unit 2, we took advantage right there. And then we actually saw some of that in Unit 3. We saw our acetals and our imines and iminium ions and enamines. We also added into that number 2 carbon, and we used that number 2 carbon as an electrophile. And then we got a little bit bigger. We branched out just a little bit more in our Unit 3, and we started looking at the fact that aldehydes and ketones have another reactivity next to our ketones or aldehydes. We started by recognizing that enol form, and then we enhanced that by adding base. So if we just let Mother Nature have this equilibrium, remember it was something like 99% actually was in that ketone form, and then maybe around 1% was in that enol form. Of course, again, it depends on your structure. But then we could also treat this with base. If we took our ketone and we treated with base, now we could make all of our enolate. Okay, so we're going to use that vocab again in this unit. So this is an enol, nice and neutral. We let Mother Nature take over that one. And then here we actually made that happen. We used some sort of base. This is our enolate. Okay. And then when we formed that enolate, what happened to our reactivity? Well, now we switched reactivity, and we now are using our enolate as a nucleophile. Except where does it react? If we push our arrows, it reacts on that carbon right next door. So right there. So we can react with all kinds of things. We did enolate chemistry in our last unit with alkyl halides, and we did a nice SN2 that way, and then we could add in right next to that ketone. So that is right here in this chemistry. If we actually use some base and we develop an enolate, we can react with electrophiles. And we saw in that unit we could add in aldehydes, ketones, alkyl halides. Oops, spelled wrong. Wow. And we haven't quite done this one yet. This will be another video, but bromine, that's the haloform reaction if you want to look that one up. That is coming. That's also a good way to make a carboxylic acid. So that is on the way. So we've got lots of reactivity already, and I tried to color code this so maybe I could help you with your cheat sheet. And then where are we headed in this video and in Unit 4? right here. So what did we kind of end our aldol reactions with? Oh, what? Let's put a generic aldol up here. What if we ended with our little substrate like this, 1, 2, 3, and then we treated that with some heat? Look at what we ended up with there. We've got that double bond in there. And we commented in our aldol that that double bond will always end up in the same place. It has that spacing alternating, and it is in conjugation. So it's really, really particular that these compounds are in conjugation. This next series of reaction, they're called 1,4 additions. You can see the numbering of my 1, 2, 3, 4. That's what that means. They are also called conjugate additions, and I'll probably goof up and call them both. They're conjugate additions because they only work if they are in conjugation with a ketone or an aldehyde. So this is where we're headed. This is going to be so much fun. I love it because it's 2 for the price of 1. You've already done the aldol chemistry. It's the test you're taking right now. So we get to take the aldol chemistry and go do something with it and get it a little bit more complicated with only one more step right after our aldol. That's really exciting. So let's kind of scroll down a little bit. I wrote a generic aldol in here, and I thought we could just kind of start there and draw a mechanism. So our generic aldol, this was our unit 3. Colors. This is our unit 3. This is the test you're taking now. This is our aldol. Again, we could do a nice mixed aldol and just do this with heat, or we could use base and do a directed aldol. We've got 2 different options. I went ahead and just picked our first example, our most simple, and I took acetaldehyde right here. And let's just review a little bit. Let's draw out what would happen in that aldol. Remember, we would view that as being in that enol form as well. So we've got both of these in solution. Even if we've got only a teeny amount of that enol, you still have that enol. And then every single aldol that we have, we number 1, 2, 3. This is our nucleophile side. This is our electrophile side. And then in our mechanism, those electrons always form that bond between 2 and 3. And our numbering helps for the aldol, always 1, 2, 3. Your oxygens end up on 1 and 3. You can always tell your spacing. You can always draw your product. You don't even have to draw the mechanism. Your nucleophile, you get your double bond back. That is what that arrow is right there. You reform that double bond. So here's my 1, 2, 3. And then from that aldol, we had the second option. Sometimes you eliminate water from those. And in this case, let me draw the OH there first. So this is what we would make. And if you have hydrogens here, and you add a little bit of heat, sometimes you need heat, sometimes you don't. Sometimes that just happens because that is favored. You now make that conjugated alkene right there. This is not a normal alkene. This alkene is not just any old alkene because it is connected through conjugation with that ketone. So these are very specific substrates. Oh, they get a sparkle pen. These substrates are very specific. We still have that 1, 2, 3 spacing, but we also are in conjugation with a ketone and an alkene. And these are perfect for our 1,4 additions. It turns out we can add an awful lot of nucleophiles, 1,4, into that system. And what's really cool about it is that we can add things that maybe we haven't added before. So it's going to be pretty fun. Hit pause if you need to. I'm going to scroll down just a little bit, but I kind of want to erase what I just wrote. So hit pause or take a screenshot real quick if you need to. I'm going to erase right here. I want to draw the 1,4 addition part. All right, and I love that it just goes right with the aldol. We are taking that test right now. Now we just get to expand it. It's going to be so much fun. Okay, so let's take that product of the aldol. Let's take our conjugated product here. Awesome. Now we can use a variety of nucleophiles. We can use cyanide. We can use amines. We can use Gilman's. Let's do all of those first. And then finally, we can actually use other enols or enolates. Oh my gosh, that's where chaos happens, and it's going to be so much fun. Let's start with a nice straightforward one. Let's take cyanide. We've seen cyanide all the way back to OChem 1. Cyanide is a phenomenal nucleophile. We'll see it in Unit 4 and Unit 5. We're also going to use cyanide to make carboxylic acids. So we will also take cyanide and nitriles and turn them into other functional groups. So that is a big unit for us. So let's start with some chemistry on some cyanide. Now, in general, when you use cyanide, you tend to buy the salt. You can get either sodium cyanide or potassium cyanide. We'll talk about the safety of cyanide when we hit one of my favorite reactions, the Strecker reaction, and we make amino acids. Cyanide itself is quite toxic. When it's in the salt form, it's at least in solution. If you treat that with any kind of acid, now you're going to make the gas, HCN. That is phenomenally toxic, and you do not want to breathe that in. At least if it's in a salt, you can block the inhalation if it's in solution, but HCN itself is a gas, so you want to be extremely careful with this kind of chemistry. So let's take our cyanide, and we know out of any of those sources, let's just start with sodium cyanide. Out of any of those sources, what we're really looking at is we've got nice valable electrons on carbon. We've got a negative on that carbon. Our size is small, linear. It's a great nucleophile, and if you mix it with one of our aldol substrates, it does not go here. It goes here. Okay, holy crap. How does that happen? That looks pretty crazy. You know, that would never happen on a normal alkene. Oop, I feel a listing moment. If I were back in OChem 1 and I wanted so bad to try this reaction and I just stirred these two up, oh yeah, I would get nothing. No reaction on that one. The reason this reaction works, the one that we're looking at, is the ketone. This is still the driving force in that reaction as far as being an electrophile. You still have that polarity. It's just connected to that double bond also. So watch my arrows. This is going to be fun. Cyanide has a place to go. These electrons have a place to go. We form that bond to carbon, and then these pi electrons, this alkene, they are connected. They have a place to go. Those electrons can go all the way up to that oxygen. This is awesome, and this makes sense in terms of electronegativity. Out of all of this, oxygen's the most electronegative. So where do those electrons end up? They end up right around oxygen. Okay, so let's draw the product of that. What did we just make? All right, we've got our oxygen still here. Now it's a negative. Our double bond is now here, and we just formed a bond here to cyanide. Okay. All right, now what do you do with this enolate? Well, typically in these solutions, you have something in there. So whether it's water, whether it's a little bit of an acid quench, we would likely write our cyanide as number 1. Again, you don't mix acid and cyanide together, so you would react your cyanide first, and then you would add some sort of an acidic quench to that. And where you quench is actually this double bond. So we would quench here to here. All right, let's draw the product of that. All right, our oxygen stays. We just formed a bond down here to hydrogen and up here to our cyanide. Okay. So out of that whole process, you actually had electrons flowing through that whole system. That's what makes that 1,4 addition so special, and why it couldn't happen if you didn't have the ketone. Your electrons go all the way up to that oxygen and all the way back down, and you quench. And then I feel like I need to just write this a little bit nicer, and we need to talk about our spacing. Does anybody notice what we just did? We just added a different nucleophile right in that number 3 spot on an aldol. So this is pretty awesome. This is very connected to an aldol. This is something in synthesis that you can make an aldol with one step, and you can add a different nucleophile there with a second step. Really useful for that chemistry, really useful. What's another one? Let's do one more. Let's do an amine. So take a screenshot real quick. I don't think I left myself some more space, so I think I need, oh, no, I left myself space. It's like I planned ahead. Okay, let's take that same substrate, only this one, I'm going to put this one in a ring. You know we love rings in organic too. When in doubt, draw a ring. You know, if you want to make organic too hard, put a ring in it. So let's take one of our substrates with a ring, and then let's treat this with nitrogen. Okay, now hang on a second. We've done this. We've done this before. What happens if you have a ketone and an amine? Well, this is a recipe. Let's compare. This would be an awesome test question for the test you're taking right now. What in the world would we make? We would make that amine. Awesome. Okay, but then, holy crap, what happens if you have that double bond in conjugation? Ammonia will actually end up 1,4. All right, let's draw that mechanism. That's fun. All right, so instead, this time our ammonia, whatever form that ammonia is in, that could be ammonia chloride, that could be ammonia, that could be all kinds of forms. That could be like this. We've used that a lot in our mechanisms. That ammonia, this time, is going to add right here. That alkene has a place to go. It is going to go there. And then these electrons flow all the way up to that oxygen. So in our 1,4 addition, let's look at our electron flow. Let's draw that a little bit bigger so you can see it. We just made that and that. Okay. And then again, we will have some quench steps here. We'll either have some little bit of acid in solution already in this reaction, or we'll have a quench step. And then let's draw the product of that. Okay, so now we've just reformed this bond. We've quenched here, and we've ended up with our nitrogen there. All right, now the charge here is going to depend on what you started with and what your quench step is. So we can also relieve that positive charge if we had our little bit of any kind of base in there, if we had a little bit of free ammonia, anything in there to relieve that positive charge. So at the end of this whole process, we just added a nitrogen right there. Wait a second, I'm having a connection moment. This is also 1, 2, 3. Well, wait a second, that's on our last test. So depending on your substrates, you now have 2 different ways to have a nitrogen in that 3rd spot. What is the other way? It's in unit 3. It's the reaction we're testing on right now. Manic reaction. So it just depends on your substrate and how you want to make that happen. We could do a 1,4 addition with an amine, or we could do a manic reaction. Both of them give your nitrogen in that spacing. That's pretty fun. All right, so let me pause this video, and then we're going to take